Why? Anybody know? What makes it a difficult problem? Yeah? That means what I'm saying is 0.00000002 is not the concentration of H. It's definitely the concentration of Cl, but not of H. Why? Seems like it's going against everything we know about strong acids, right? If that's not the concentration of the H, then what is? How do you get the concentration of the H? We've never been worried about this before. Is this in water? Is this problem in water? Yeah, I mean, we never say they are, but they're always aqueous solutions, right? So it's in water. There you go. There's a contribution to the concentration of the hydrogen ion from the water itself. Well, it's going to be somewhat acidic solution, but it's going to be on the order of 10 to the negative 7, a millionth of a molar, right? Extremely small, but that's going to contribute to this number. It's going to make it a little bit bigger. So your pH is going to be off. You may not care, but you will care if all of the little fishies or everything in this research project or everything about designing this chemical, very expensive drug won't work if the pH isn't right, right? So little changes can affect little things in a big way. It depends on the problem. We have to pick it out. What's the pH in 0.085 molar H3PO4? So this one is tough. Top one, tough, because you have the contribution of H from multiple sources. How about the purple one? Now, first, let's hit on that thought first. The concentration of the H, you see 3 H's, just take 0.085 times 3 and be done with it. Won't work. Why? Can you see it? No. What are all the species in solution? Think about all the locations that H is tied up. It's tied up in what species? What ions? Okay, water? Yeah. Now you have the contribution from water falling apart, right? But look, this is 0.085 molar. Maybe we don't care, but we can still throw it into our systematic treatment of equilibrium. We can, but we may not need to worry about it. But what are the other? Do you see where H is tied up? Do you see why we can't take 3 times 0.085? The answer is going to be a lot less, because H is also tied up where? Do you remember writing Ka1, Ka2, Ka3? Yeah. Oh, there's one. Where's my pen? Someone said one of them. One of them. H2PO4 with a negative. A lot of H's are tied up there. That's a weak acid. That's going to be a very appreciable amount. What other forms do you have that have HPO4 negative 2? How about this compound itself, H3PO4? Is that going to be a species in solution? Yes, and you know why? Definitely yes, because it's not on the list of strong acids. There's going to be a lot of there's going to be more of H3PO4 than anything else. It's a weak acid. Right? Now, we could write down PO4 minus 3, but we don't really care because that's not tying up any H's. So what's the concentration of the H? 5-step program. Figure it out. What's the concentration of carbonate in a solution containing calcium carbonate solid, 0.34 molar carbonic acid, and 0.013 molar HCl? Right? Notice how all these things are tied in with one another, aren't they? Like you'd think oh, the HCl doesn't have anything to do with anything. Well, yeah, it does, because carbonic acid is a weak acid. Equilibria, chemical reactions like to form stuff that are nice and stable and stay there, right? A solid is one of them, but so are weak acids. You dump in some HCl, that's going to interact with the equilibrium going on here, like common ion effect, you want to think of it that way. While the amounts of carbonic acid is going to interact with the KSP problem you're going to have over here. All this stuff is interrelated, right? Complex problems. Okay, so how are we going to handle them? Well, let's do a little review first. So, Kimberly came in, and man, I just kept writing and writing and writing, right? She inspired me. Sorry. Okay, so some of this stuff is new, some of this isn't. Write the general equilibrium constant expressions for Kw. Okay, how do you write Kw? John, how do you write Kw? Oh, let's write the reaction. Let's write the reaction first. Yeah, but it's... Yeah, what's the reaction for Kw? H2O goes to H plus and OH minus. It might be easier to start there and then you write the Kw expression, right? Should have asked that first. Okay. How do you write the Kw for that then? Danielle? There's our reaction. So Kw would be just like Pedro said, products over reactants. Yeah. And then we quit, right? Yeah, there's our Kw. How about a Ka? Adriana, how do we write Ka reactions? Or, yeah, let's write the reaction first, then the Ka expression. Okay, so how do you write the Ka reaction? Yeah, that's what. Remember, that's what we used. HA is what we use for our general all reaction, all acids. You got the H and the A, right? Okay, keep going. That goes to H plus and A minus. All right. So then we can write our Ka, John, and that's going to be concentration of H plus, concentration of A minus. Yeah, because it's not a solid or a liquid. Right? KSP. Kimberly, how do KSP reactions always go? Yeah, right. That's going to be the KSP. So the reaction is what? The solid is on which side then? Yeah. Reactant side. Because she said it's 1 over, right? So solid going to the ions. So KSP's... Oh, it's not 1 over. It's going to be the ions on top over 1, right? Oh, yeah. Formation constant, yeah. Well, we're not worry about them. Okay, so this is just a reminder how to do all those. We're going to need it. Writing charge balance equations. Okay. The whole game plan for all of this, by the way, is if you have Pablo, when's the last time you took an algebra class? Probably a long time ago, right? Okay. You have this funky equation, 6x squared plus 7y minus 8z equals 12. Right? You have an x and a y and a z. It's making this stuff up. How many equations do you have to have? How many equations do you have to write down to enable you to solve this? 3. The number of variables, the number of unknowns has to equal the number of equations, right? So you get all these bloody equations. Then it's all algebra. You solve one for one, substitute into another one, right? So you see what's coming? That's exactly what we have to do. We need to learn how to write a bunch of these equations. Okay, and in the end, hopefully the number of equations equals the number of unknowns, and then we do our math. Charge balance equations can be written for a solution that contains charged particles. So you can't write a charge balance if there's nothing that's charged. Because the overall charge of the solution is, Adriana, it's 0. Yeah. Solutions aren't overall, they're neutral, right? Okay. Write a charge balance equation for a solution containing. So we really don't care what the compound is. All we care about is its charge. And the game plan for this is to write all the cations on one side and all the anions on the other side. And for example, if I have a phosphate, the charge on phosphate is -3. So we're going to take the charge times that guy's concentration. Because all we're worried, we don't care about phosphate. We care about charge is all. So let me show you what this looks like. Let's write all the cations on one side. So we have Na+. We have, what's another cation? Is that my only one? That's my only one. Okay, well, that was easy. Okay, all the anions on the other side. So list them all out. Chlorine, phosphate. There's that HPO4 -2 thing. And I have H2PO4 minus. Okay. Does this compound, phosphoric acid, have a charge? No. So he doesn't belong in the charge balance. There's no charge for him. Because what we're going to do, because really all you're doing, you're taking the charge and multiplying it times the concentration and setting it equal to 0. That's all you're doing. Since H3PO4 doesn't have a charge, you're taking 0 times its concentration, you get 0. So what we're going to do is take a 1 out front for the sodium, a positive 1, right? A 1 times that guy, a 1 times that guy, a 3 times that one. See what I'm doing? It really doesn't. You can if you want, but no. I think this is, we can, if you want to do put the negative sign out front. See, I guess I did a step ahead for the algebra. You multiply bring all these guys over to the same side, right? So you'd have a positive 1 times Na+, a negative 1 times Cl minus, a negative 3 times PO4 minus 3, right? But if you bring it all over to the other side, it would look like this. So I kind of skipped a step in the algebra. Because all the charges have to add up to be 0. So I guess I did it this way, Anna, because it's easier to recognize and write charge balance equations. Put all the cations on one side, all the anions on the other. Okay, so to me, it's easier to remember. But you're right, you're exactly right. You should be writing a -3, but they should all be on the same side, though, equals 0. Is really the way you should do it. You're right. Okay. So okay with writing charge balance equations? Mass balance equations. This is a little more, a little more odd. I don't know, there must be a better way to word this. I think it'll make more sense after we see it. Mass balance equations take into account the fact that when the concentration of a salt is known, the concentration, now what's a salt? Sodium chloride's a salt, but it has a cation and a anion. It's all salt. Something has a cation and an anion. Okay. The concentration of the cation in all its forms in the solution is equal to the concentration of the anion in all its forms in the solution. Well, all I'm trying to get at is this word forms. So this is wordy, but let's do some problems that will make a lot more sense. So these mass balance equations are also going to be easier to write in an actual problem because we're going to identify all the ions in solution before we get this far, but that's okay. So all we're saying is that the concentration of sodium, cation, in all its forms has to equal the concentration of chloride in all its forms. So what are all the species? So it's easiest probably to list them all out first. Do I write, is NaCl a species? Does NaCl exist in solution? Is that going to exist? It's completely soluble, so does it exist? No, he's not. He doesn't exist. Don't include him. Okay, so you identify all the species, and then the concentration of sodium in all its forms. So you find anything with a sodium in it, set it equal to anything with a chlorine in it. Well, there's nothing really to pick, right? So these are going to be the same. Concentration of sodium equals the concentration of chloride, which in this case is what number? 0.001. So we've kind of seen that before, and played around with this stuff, but we haven't seen this stuff like B. Okay, when you're looking at B, you can still play the games you played before. Is this a compound that's completely soluble? Yes. And I'm not giving you solubility rules, but what I have given you a bunch of times, and you should burn it in your head, this group 1 with anything is completely 100% soluble. Yeah. So what is the concentration of sodium? What is the concentration of sodium going to be? 2 times this number, right? Those tricks still work. It's going to look uglier up here, but that still works. Okay. All right. So, well, we can write it. It doesn't hurt anything. 0.001 times 2 is my concentration of sodium. Okay. But let's handle it the way we did over here. Right? Okay. What are all the ions present in solution in this? We have Na+. What else do we have? Sulfate. Is that it?
No.
It's not it. What? Ions. Ions. No, sodium won't combine with anything. They want you to be able to recognize this kind of stuff. If I have Cn minus, I think this is what was on the test. If I have 0.2 molar cyanide, or sodium cyanide, what's the pH? How did you have to handle that question? Well, we better get an idea. We'll get it. How did you have to handle that problem? What's the pH of 0.2 molar NaCN? Last test. You have to write a KB. You had to write a KB reaction, right? You had to write a KB reaction. The reason why, because they're assuming that you're recognizing this stuff. You don't care about this guy? Oh, but this guy, he's an anion. They're all conjugate bases, every single one of them, except only 6 of them you don't worry about. There's one of them, right? There's no KB reaction for him. All the conjugates of the strong acids, you don't care. You can't write a KB for. Everything else you can. So that means Cn is present, but Cn is also present in what form? HCN. That poisonous cyanide is also present in the form of HCN. Now we're getting it. Okay, so we have HSO4 with a negative. Do we keep going? The problem with H2SO4 is that it's a strong acid, so you can't list it. Okay, so here they are. This is sulfate in all of its forms. There's only 2, but the point is there's 2. It really complicates life. Okay, so now we can play the game. We can write it this way. 2 times 0.001 is sodium. That works. Or you could write what's the concentration? What's the concentration of sulfate in all of its forms? Well, sulfate in all its forms is going to be SO4 negative 2 and what? HSO4 minus. So there's sulfate in all of its forms. Now look at this. Sulfate in all of its forms has to equal what? 0.001. Why isn't it 0.001 times 2? We only have one of them. It'd be nice, it would really be nice if we did this, but we don't. If we wrote parentheses around every single polyatomic ion whenever we saw it, but we don't. All right, there's a 1 right there. There's only 1 sulfate for every 2 sodiums. So the concentration of sodium in all its forms is twice that of sulfate in all of its forms. So this should only be 0.001. Okay. So there's a couple of equations. Mass balance equation to be right. Charge balance, put all that cations on one side, anions on the other. Put the charge out front. Mass balance, identify all the species, and then just recognize, okay, the cation in all of its forms has to equal, you can kind of figure it out. Concentration of sulfate in all its forms has to equal, kind of figure it out. Okay. So we're going to spend 2 days on this. Our 5-step program. Right, there they are. We are only going to do the first 4 steps. Right? And the goal of those first 4 steps is that step 4. If you have 4 unknowns, you better have 4 equations written by that time. And then step 5 will be to solve everything. Okay? So let's see how many of these we can get done here. Step 1 is to identify all the pertinent species in solution. So let's start with A. Identify all the pertinent species in solution. Okay. So Kathleen, what's something present in solution? Now we probably need, we do our darn solubility rules. What's the last day that we had those so you can take a look at it? Do you remember? Isn't there a, we're on 15, was it 2 days ago? Oh yeah, I never use this chart. Yeah, here it is. Yeah, I never use this chart. Okay, you're right, that's day 13. Okay, now this is helpful because I think the question was strontium nitrate, wasn't that it? What did it say? 0.2 molar or whatever? 2.8 molar strontium nitrate. So the question in my mind, well, it can't be a solid because it says 2.8 molar anything, right? It's a solution. So it can't be a precipitate. But look at the solubility rules. Nitrates form solids with nothing. So you can never form a precipitate with a nitrate, right? All right? All right. What's another one? Acetates. Nothing, right? Look at that, cyanide. I didn't know that. Huh. Yeah, see, I should use the solubility rules more often, this guy. He's very different than the format I'm used to. But anyway, nitrates, never. All right, that's okay. So the point is, identify all the unknowns. So saying strontium nitrate's solid doesn't work. Plus, there's no equation you'd write for it anyway because he doesn't show any K expressions. So he's not a pertinent species. But it's not a KSP problem. What would be some of the ions present? Kathleen. Where's Kathleen? What's that? NO3 minus. That's a good one. That's a pertinent species. Something present. What else is present, Kat? SR. With what charge? +2. The formula tells you. Right there. Okay. You're Andy? Anything else? Okay, now you're thinking right. If you're thinking HNO3, you are thinking exactly how I want you to think. You want to think, okay, are there any other forms of this dude? Are there any other forms of this dude? So you're thinking Kas and you're thinking Kbs. That's exactly what you should be thinking. But you got to stop yourself when you see HNO3 because it's a strong acid, so you don't list them. So that's it. Okay. Now, if you're really paying attention to what I've been saying, is he in water? Yes. So that means we could just as well start writing H pluses and OH minuses. And you can. If you do that, it's just going to make the problem longer. You only introduce pertinent. You only introduce species that you're going to need to solve the problem. If you introduce H plus and OH minus, it's just going to lead to more equations we have to write. Which is fine, but it's not going to affect our answers to the problem that whatever we're after. Okay? So we kind of quit. We do quit. So that's step 1. Step 2. Jeff, we have to write any KW, KA, or KSP equilibrium constant expressions. Can we write any KW, KA, or KSP with these guys? No. Okay, because it's a conjugate. If anything, you would guess KB, but he's a conjugate of a strong acid, so he doesn't. The KB doesn't exist. So there's nothing he can do with. There's nothing there. So there's really nothing to do for step 2. But Adrian, step 3. So step 2 is done. Step 3, write a charge balance. So what would you write? Well, all the what on one side and all the what on the other? NO3 negative on one side, and the strontium on the other. No. Just make sure you do what out front? Put the charges, a 2 and a 1, right? Mass balance. Okay, charge balance just doesn't have numbers, doesn't have molarities in it. But mass balance, that's where you start playing with actually getting numbers. Bless you. So Miriam, how would you start writing a mass balance here? .8 big M equals if you pick the NO3 minus, see you have 2 of them. So it might be easier instead of messing with nitrate, mess with the strontium. So 2.8 molar. I mean, you can. You just have to put a what here? A 2. That works. But I was expecting her to say that this equals strontium. But either one works. And we can, but do we need to? Because if you go down to step 4, we only have how many unknowns? 2. We already have 2 equations. Yeah, because we have 2 equations, 2 unknowns. We can quit. Yeah, right? Okay, let's try the next one. So we're starting out, a lot easier.
So this is already solved because we already have the answers to the concentration.
Yeah, because you know how you know that strontium is going to be 2.8, and then put in 2.8 for strontium, you'll get nitrates.
Oh.
Right? Right? Does that make sense?
2.8 times 2.
Yeah. Okay. You see? Is everyone following so far?
Yeah.
Make sure you stop me if you don't, right? Okay. So Miranda, I'm trying to set it up so you don't need to worry about memorizing solubility rules, and that's where this hint is coming in. Saturated aqueous solution. Another hint, you have an S down there. Okay, but we have to start at the top. Step 1 of our 5-step process. Identify all pertinent species. What would you say is a pertinent species? PB plus 2. Good. Ooh, and Cl minus. Yeah. That's the right thinking you got to do, though. She was ready to put HCl, but she crossed it out because you recognize it's a strong acid. Good. Any other species? Mm-mm. You can do the H plus for the water and the OH minus, water falling apart, but again, you have to introduce more equations then. Jeff?
Like for the cations, are there always going to be one species for the cations? I guess R plus 2, P plus 2.
You see what he's driving at? I think you're getting onto something, because that's true. It's the conjugate base, the anion, that can grab an H and can have possible other species. Because this is positive. This can't grab an H. Okay. Now we're supposed to write, Nyla, KW, KA, or KSP? Yep. So the KSP equal the number. We get it from a table. And that has to equal what, Nyla? Uh-huh. So close. Yeah. Squared. Right? And if you're not sure how to jump to this, just write the reaction. It takes 2 seconds, right? Solid going to its ions. Are there any other KAs or KWs we can write? Nope. No KBs, nothing. Okay. Oh, I just noticed something up here. Notice that. Why is KB not listed? It's if we write a KA, we can also write a KB, but it's not introducing any new information. Right? If you write a KB, well, there's no point in writing the KA. You're just adding one more unknown and one more equation. If you really take a close look at it. Not in my 5-step program. Put it that way. Okay. Charge balance equation, Natalie. Charge balance. PB plus 2 equals. Oh, she just put the 2. Right? The charge comes out front. So the 2's just on the wrong side is all. So the charge comes out front. So you'd have a 2 over here and a 1 on the chlorine. Right? Okay. Casey, do we even need to ask the question of writing a mass balance? No. Why? There's no point. We have 2 unknowns, 2 equations, quit, do the algebra. Okay? C. Yeah, you're gonna have to oh. Do ice? No. This is just blind algebra. That's all this is blind algebra. You get in a number for KSP, right? And put that number in. We know that Cl is 2 Pb plus 2s. So where you see Cl up here, put in 2 Pb plus 2s. You got to square it. Then you have an equation with just Pb plus 2 in it. You find it. And then you come down here and get the chlorine. Does that make sense? That's day 16. We don't want to jump ahead. Why do extra work? Right? Not tomorrow. It's Monday. So we'll worry about solving and doing the algebra. We'll practice all that later. Right? Let's just set stuff up. NAF. All right. Anna, what are the species present? Let's get through this one. This is the... Na plus, yeah. And F negative, HF. Now here's one where, right? Right? Now you know what's coming up. You know that you're going to have to write a Ka. That means you're going to have H pluses. That means, right? And I'm just adding them now instead of later, because you can write the reaction and then go back up and write it. But well, if you have H pluses, you're also going to have OH minuses. Now you're on the same page as me, right?
Why are we putting this time?
Well, because I can see that we're going to have to write a Ka reaction. If you have a Ka reaction, you have an H plus in there. And then if you have an H plus, now this darn Kw thing is going to come into play. So you might as well write OH right away. But you can save them. Write Kw, you end up writing Ka. Oh, I'm missing H plus. Write it up there. I'll write the Kw. Oh, I'm missing OH minus. Write it up there. But I say whenever you're going to have to write a Ka, just throw the H plus and OH minus up there. Okay. We're supposed to write any Kw, Ka, or Ksp. So we're going to write a Ka. Ka equals products over reactants. H plus, bless you, F minus, all over HF. Do we write a Kw? Yes, because see, we have our H plus and OH minus. Kw, H plus, OH minus. Right? Charge balance. All the cations on one side, anions on the other. So let's throw sodium and H plus on one side, anions on the other, and that's just F minus and OH minus. Does it have a charge? Does it have a charge? If it doesn't have a charge, HF. You have to see that. That's very often hard for folks to see. Does this have a charge? No, it can't fit in the charge balance. Think of it this way, Nyla. Put a 0 times the concentration of HF, because that has no charge. You always multiply the charge times the concentration. All right. We have how many unknowns, everybody? 5. How many equations? 1, 2. We need 2 more. We have to mess with mass balance, right? Okay. So do you see what one of them is? 2.1 molar has to equal what? Ooh, that's what I'm thinking. Na plus, in all its forms. Look at your listing up here. Is there anything else with sodium in it? No. So you're done. We need one more. 2.1 equals F minus F in all its forms. Exactly. And if there were more of them, you'd have to throw them in. 5 equations, 5 unknowns. We're done. So see if you can finish this for homework, right? Just stop here for day 16. Okay. So check out the homework on the assignment schedule and finish this up through day 16. Oh, yeah. Sorry.